215 and 244. Okay, let's go back and find 215 and 244. Okay, so in this circuit, you have to find what? X sub L, right? So what is X sub L? This is 215. J 2 pi F L. So L is 33 millihenries, frequency of 40. So 2 times pi times F times L. So it's J times 2 times pi times 40 times 33 times 10 to the minus third. What is that? 2 times pi times 40 times 33 is equal to times pi times 40 times 33 is equal to. So it's equal to 8.293, right? J 8.293 ohms. Is that right? Is that what you got? Okay. So we have I is 2 amps. So I is equal to 2 peak to peak. So you just label peak to peak, or just label it 2, and remember it's peak to peak. And then I times X sub L is equal to V. V times I times R is equal to V. So basically it is 2 times 8.293 J is equal to V. What is V? 2 times 8.293 is, excuse me, 16.566. Now, it's got a J with it, right? J means 90 degrees. So what? So if I is equal to 2 sine of 2 pi times 40 t, V is equal to 16.566 sine of 2 pi times 40t plus 90 degrees. Is that right? Everybody got that? Any questions about number 15? Nope. All right, that should be your answer. Number 44. All right, so determine VB, VC, and VAC. Okay, so this is one where you don't have to do the 2 pi FL or anything like that. It's given to you. So this is J400. This is 1 volt, plus on the left, minus on the right, and that's A. This is B, and you have 800. This is your reference or your zero down here. This is 0 volts down here. This is 800, and this is minus J, 1K. All right, so the very first thing you should do, this is 1 volt. And do they say peak or do they say it's peak? So this is 1 volt peak. So everything is going to be in peak. So I is what? I is equal to V1 over, because this is in series, Z sub Z total. So Z total is equal to 1 divided by 800. And which way is I going? Is I going this way, or is I going to the left, right? Okay. So it's 800 plus J400 minus J1K. So it's equal to 1 over 800 minus J600. Anybody have any problem with that? So what is I? 1 divided by parenthesis 800 minus 600 I parenthesis equals option down 1 equals shift equals, it's equal to 0.001 or 1 milliamp at angle 36.86 degrees. And that's 1 milliamp at angle 36.86. Now, if it's going in this direction, the plus is on the top, so VA is equal to I times J400. So what would be VA? It's 1 milliamp at 36.86 degrees times J400. What is that? 0.001 angle 36.86, and you can put that in direct, times 400 I equals option down 1 equals shift equals, it's equal to 0.4 at angle 126.86. That's VA. What is VB? Well, it is equal to VA, VB is equal to VA minus 1 at angle 0. Okay? So you do that. So you say VA is 0.4 at 126.86 minus 1 at angle 0, and what do you get? VB is, okay, so that is VB. That VB is that. It's 1, excuse me, it's 0.4 at angle 126.86 minus 1 at angle 0, or just say minus 1 equals, option down, 1 equals. So VB is, nope, I got it wrong. Okay, so let's do it again. 0.4, no, it may be right. 0.4 at angle 126.86 minus 1 is equal to minus, okay, so option down, 1 equals, shift equals, it's 126, 1.28 at angle 165.52. Is that right? Is that what you got? Okay, anybody not get that for VB? All right, then what else do they ask? VC, so what is VC? Well, it's VB, VC equal to, VC now is equal to, if the current's going like this, it's equal to a current of, right here, but it's going to be minus, so it's going to be, VC is going to be, current is coming from the bottom, so it's going to be a minus 1 milliamp at angle 36.86 times minus J1K, all right? So what is that? Minus 0.001 angle 36.86 times a minus 1,000 I equals, I'll get it, minus 0.001 minus 0.001 at angle 36.86 times minus 1,000 I equal, they still give me an error. Okay, I'm just going to say 0.001 angle, because the minuses cancel each other out, times 1,000 I equals, option down, 1 equals, star equals, so VC is equal to 1 at angle 126.86. That's VC. So VAC is equal to VA minus VC, or VA minus VC. So it's 0.4 at angle 126.86 minus 1 at angle 126.86. So it's 0.4 minus 1. 0.4 at angle 126.86 minus 1 at angle 126.86 is equal to 0.6. So VAC is equal to 0.6 at angle minus 53.14. I probably won't ask you one exactly like this ever again. This is kind of a strange one. Okay? Did anybody get exactly those answers, pretty much? Did you? Okay. All right, so if you got something even halfway close, or it looked halfway close, I gave you credit for it, okay? This is not an easy one, and I didn't expect you to get it all the way through, all right? But that's one way of working it. It's not the only way of working it, but it's one way of working it. And anyway, so anybody have any questions? No, going ahead, right? Move on quickly. All right, so we're into chapter 5. If you haven't gotten through chapter 5 and looked at it, please do. I'm sure that most of you have done this stuff before, but this is, if you have not done Thevenin before, it's the two parts on top of each other that get you, that it's doing everything with complex numbers and then going in and doing Thevenin, which by itself is not hard, but doing it with complex numbers seems to be a hard thing to do. So anyway, that's okay. So let's start working a few problems in chapter 6. Excuse me, chapter 5. All right. Okay, let's just review it for a few minutes before we get into the problems. So when you see a problem like this, and you basically are asked to solve for it, like if you want to find the current through the last thing on the right-hand side, what you do is you cut it out. In other words, you take scissors and you cut this resistor off. Just take it out like that, okay? So you take the component out, then you find the voltage across these terminals, and then you find the Z looking from C backwards into the circuit to this D, from C to here. So you travel backwards. You start here, you come down here, then you go this way or this way. This is a parallel circuit, and then you find the Z total. Then you put it back together again, and that when you put it back together again, you put it back together with that put it back, but with Z and V, your new Z and V, okay? Now you can do this anywhere in a circuit. You can cut out any component. You do not have to cut out the component on the right. You can cut out a component in the middle. It doesn't matter. And like I said the other day, you can actually do this measurement in laboratory and you'll get the exact same result. Why is it hard to do in a laboratory with components like this? Because your Z's are dependent on a frequency, aren't they? And you have to have that device in there in order to get that frequency. You can't measure with an ohm meter and get these values. You have to have that frequency in order to get those values. In other words, you have to have the device in order to get those values for those Z's. But that being said, this process works, okay? So That's superposition. So this will be probably the hardest part of a test because you're dealing with Z's instead of R's, and you're dealing with Thevenin and Norton, which you may or may not have learned. Maximum power theorem says the following. If you want to get the maximum out of a circuit, in other words, if you want to maximize from here to here the power, you match the Z to the Z. But you don't match it exactly. You match it, if this has got a plus I, this is a minus I. It's called the complex conjugate. All right, so if you want to get the maximum power out of a resistive circuit, what did you do? You had matched this R to this R. These were equal. All right? But in this circuit, if you want to get the maximum out, what you do is you say, okay, I've got an AC source and I've got a Z up here, okay? How do I get the maximum bang for my buck out here? I do what we call Z star. So if this has got a real plus a J imaginary, this is the real minus the J imaginary. Okay? So to get the maximum bang for your buck, you've got to match the R and you've got to complement the J. You got to do the opposite. All right? It's called the complement. Hi, you're looking good today. Oh, that's the wrong complement. That's a C-O-M-P-L-I-M-E-N-T. This is C-O-M-P-L-E-M-E-N-T, complement. Anyway, trying to be funny. It's not a funny day, right? This is the plus J, this is the minus J, or if this is the minus J, this would be the plus J. This is called the complement. It's the complex conjugate, but it's the complement of it. The real name is complex conjugate. But it's also called the complement. All right, now, this is the graph of what you get when you get the complex conjugate. You get a peak in power. And that's shown here as well. So, if you had this, what would be the load that would give you the peak power? 20 minus J10, right there. That's what you have. That would be the name. That would be what you would have to do in order to get the peak power out. So, if that's the case, what would be the peak power out? You have to figure that out. All right? And again, this is not hard. The hardest part here is the Thevenin. Now, this part, delta to y and y to delta, I'm just going to tell you, we're going to skip. But there are equations for the conversion from a delta to a y or a y to a delta that are valid. But we're not going to memorize them, and we're not going to expect you to memorize them, okay? So there are, if you have a 3 points, and this is a delta. You have 3 points, and you've got a Z here, You've got a z here, and you've got a z here. All right? ZA, ZB, ZC. You can convert that to a y. And they aren't equal. They are not equal. So this ZA, this ZB, this ZC is not equal to these three Z's. They're not equal, but there is a conversion that you can find between the two, and these equations are listed in here. There they are, but I'm not going to ask you to memorize them, and I'm not going to ask you to do those on problems. Okay, there's your formulas. There's your conversions, right? Not going to worry about them. We're not going to have problems with them, but you can do conversions between. See, there's a question for one. There it is. What is this? Is this a delta or a y? Looks like a y, although it's a t. But see you come to a common point in the middle? Okay. Now, why do we worry about this? We really don't. Except for the fact that you can hook up transformers either this way or this way. All right, you can hook up the primary this way, and you can hook up the secondary this way. Y to delta, delta to Y is a common way of hooking up transformers because you get less what we call harmonic transfer through a Y to delta or delta to Y than you do through a delta to delta or a Y to Y transformer. Okay? It's preferred to do a delta to Y hookup on a transformer, but we never worry about the impedance of those three legs. We don't worry about it. We say, okay, next, all right? We don't worry about this, but here is the transform. If at some point in time you do worry about it, there it is. Right? But we don't worry about it, and we skip it and we go on. You say, well, why don't you study all this, everything? It's not needed. We don't need it for anything. If you need it, you can go back and look at the formulas, but you won't. Okay. So here is one on superposition. Now, we'll work a couple on superposition, but like I told you the other day, I'm not nearly as inclined to ask a question on superposition as I am on Thevenin and Norton. So here is a superposition question. What do you do with something like this? Well, you solve it for this circuit with this one jumpered out. Then you solve it for this circuit with this one jumpered out, and you add the two together. All right? We can do one of these, but we're not going to do a bunch. Okay. We're not going to do half a dozen of them. All right, let's do one. I can't say I won't ask a question on this, but I doubt it. Highly doubt it. Okay. So this is 5.1, and here we have a value of 2 plus to minus, and there up here is a 2.7K resistor, and down here is a 2.2K resistor, and this looks just like exactly like most resistive circuit examples, except for the fact that now we've got a capacitor, and we've got AC instead of DC. So these are peak, everything's in peak, and they're the same frequency. So that gives us some comfort level. But we've got to find the X sub C up here, right? What is it? It's 1 over J 2 pi times F, which is what? 2 pi times 1,000 times C, which is 1.5 times 10 to the minus 6. What is that? 1 divided by all that. 2 times pi times 1,000 times 1.5 equals Okay, so it's equal to 106, right? No. Okay, so I get x sub c is equal to 106.1, and that's with a minus j in front of it. Is that what everybody got? Yeah. Okay. So now we can go back and we can find, redraw the circuit, 2.7K, 2.2K, and up here we have a capacitor with a minus J 106, and we can jumper out this one. So what is the combined? They want to know VB. So VB, it would be, if we find these two together and then we do a voltage divider, we can get it. So this would be VB, this is the B point. So what would be the combined impedance of this? One divided by, parenthesis, 1 divided by 2200 plus 1 divided by minus 106 I, parenthesis, equal, what does it equal? I get 105.88 at angle minus 87.2224. Everybody get that? Is that what you got? Is that what you got? Something like that. Okay, so now let's do voltage divider. So VB is equal to 105.88 at angle minus 87.24 over 105.88 at angle minus 87.24 plus 2.7K times 2. That's our voltage at VB for the left side. All right, what is the answer to that? The magic calculator is the only way to get this. Okay, so you gotta use this calculator or else you're dead. This is not an easy one. 105.88 at angle minus 87.74 times 2 divided by parenthesis 105.88 at angle minus 87.24 plus 2700 parenthesis equals option down 1 equals shift equals, what does it equal? 0.081 at angle minus 87.22. Is that about right? What you got? Without the calculator, without a good calculator, this is impossible. Is that what you got? No? What'd you get? What's VB? It's this resistance over this plus this times this. All right? That's it. that what you got? What you got, Adam? Okay. Anybody else get it? Anybody else get that number for that VB? No? Yes?
It goes off by 2. I got -85.
But is it eight? I don't care if it's 85 or 87. Okay, you're close enough. You're close enough. Any question about that? Can everybody get this? This is valid. I mean, you say, we won't use superposition, but I'll ask a question probably like this. Okay, did you get it? Yeah, no, maybe? Okay, good. Okay, you got to do this. You got to be able to do this, right? That's VB from the left source. Now, what is it from the right source? VB from the right source is equal to what? Write the equation. It's 3 times that, times the combination of these two. What is the combination of 2.7K in parallel with 2.2K? What is that? That's an easy one. R1, R2 over R1 plus R2. I still like doing the 1 over 1 over rule, but you decide how you want to do this one, okay? It's 1 divided by 2,700 plus 1 divided by 2,200. Boom. Let me do it again. 1 divided by, parenthesis, 1 divided by 2,700 plus 1 divided by 2,200, parenthesis, equals, shift equals 1212, right? So the combination of these two is equal to 1212 ohms. Straight ohms. There's no J involved with this one. So it's 3 times that, or 1212, over 1212 minus J106. Does everybody see that when I go this way, it's this resistance over this resistance plus that? Okay, so what is the answer here? And then what we're going to do when we get done, we add them together, right? So what is 3 times 1212 divided by parenthesis 1212 minus 106I parenthesis equals, messed it up. Okay, menu equals 3 times 1212 divided by parenthesis 1212 minus 106I in parenthesis equals, option down, 1 equals, shift equals 2.988 at angle 4.99, right? Okay, now what do you do with these two? You add them together. You mean you add this to this? Yes, you do. So it's 2.988 plus 0.08 at angle minus 87.22, and there's your final answer. What's the final answer? Again, the magic calculator, okay? 2.988 at angle 4.99 plus 0.08 at angle minus 87.22 equals what? Option 1, 2.98 something at angle 3. These are terrible problems, okay? But doable, all right? I hate them. Do not like them. Right, there is number 7. Again, please do not worry about these because they're not going to be questions that you're going to have to answer. he goes way, 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 way overboard with these questions, okay? But now, all right, so now let's go down to some of the Thevenin questions. Which are valid, okay? So now, here is a question. Use Thevenin to find VB in the circuit below, all right? So it probably is the best way to find VB anyway. It says use Thevenin, but you know something? If you, whether you say use Thevenin or find, the best way to find VB is to Thevenize a circuit. If it's only the thing at the far right, it's the best way by far, okay? It is. If you only care about what is the output, the last thing on the right, Thevenize it. And that's a general rule. Right. New. All right, so what do? We take scissors and we cut the capacitor out. Okay? So now it's not so bad if we do that, okay, to find VB, because here's 500 up here. Here is a J, 4K, and here's a 2.7K. What are you gonna, whoops. What are you gonna do with this? What are you gonna do with these immediately? You're gonna make them into a box that they're equal to something, okay? And you're gonna cut this out. So this is a 2.7K. What are you gonna do immediately? You're gonna combine these two, right? Combine these two into one and make it a complex Z. So how do you do that? They're in parallel. So it's R1, R2 over R1, R2 plus R2, or use the 1 over 1 over rule, which is what I do all the time. I very rarely do the R1, R2 over R1 plus R2. I do 1 over, and that I usually get the right answer, okay? Note the word usual. 1 divided by, parenthesis, 1 divided by 4,000 I plus 1 divided by 2,700, parenthesis, equal, option 1, argument down, equal, and then shift equal. What is the combination of these two? It's 2237.89 at angle 34.01. And there I have it. That is the resistor that's hanging there instead of these two. Yes, sir. Which now?
3.9.
Oh, I haven't even written it up there. It's 3.9K, yeah. No. You combine these two first. You combine these two, all right? So what I want is I want this. That's our old favorite circuit for Thevenizing, okay? If I had this, I got it, if I can do this. But I had two here, and I want to combine them into one. So I can write the resistance of these two. Instead of a resistor, I can write this for the resistance right there. All right? Now, what is V Thevenin? This is dangling. Remember what's Perry Mason? The case of the, the case of the blah, blah, blah. Well, this is the case of the dangling resistor. That does not count when we find V Thevenin. Why? Why does this not even come into the situation when we're finding V Thevenin? There's no current through it. We clipped it. We cut the current. We cut it here so there can't be any current going out through there, so it is dead. Now, when we find R Thevenin, we have to use it. But Be a detective. This is a case of the dangling resistor. Okay? Does that make sense? Because that's exactly what you got. It does not count when you find V Thevenin. It does count when you find R Thevenin. So you're looking for, is that resistor there or is it not there? If it's not there, good. If it is there, you don't count it for V Thevenin, you count it for R Thevenin. Does this make sense? Because this is how this is done. Okay? This is how Thevenization works. Good, bad, or indifferent. This is it. And that's why when we get to this point, we stop for a little bit. We all recount how you did Thevenin in resistive circuits, and you say, it's exactly the same way. It's exactly the same way. The only difference is when you do that power thing, you take the complex conjugate, or the complement, or whatever you want to call it. It's the other brother, okay? It's if it was a plus J, now it's a minus J. That's the only difference. All right? So, what is V Thevenin? You can't chat GPT this in a test. I'm sorry to tell you, you can't chat GPT in a test. You can do it now, but you can't in a test. Unfortunately. So what is V Thevenin? Somebody give me the equation for it. Sure.
It's gonna be the Z divided plus this.
It's okay. Give me the numbers. It's 30. Okay, so it's 30 times what?
I think that's only 137. That's 137 plus.
Yep. I want. I got to get this phone. I'll be right back. You guys figure this one out. I'll be right back. Hello. Good. Thanks for calling.
So, it's the Z number plus one. So, Yeah. 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 Very good. Amazon, it's actually in maximum. So, yeah, there's just no way I would accept it. Yeah. So there's a I haven't taken over it. It's also. Yeah. I think a function on calculators. I was just saying, I just wanted to make top and the other one. So, yeah, just and just the rest of the government to locals, so we have to. Be picking certain purposes and. Yeah, mine. Awesome. Don't eat food, like store out. Cool, it's cool. See, this is like, love that. Does anybody else do this stack of homework? So. I can't believe it's. Get ready to school.
All right, did everybody get an answer for that? I'm sorry, I've been trying to battle through an issue, a technical issue, and I had to do that. Sorry about that. Okay, did everybody get an answer to that? What's the answer? 25.72 at what? 6.02? All right. Now, what's R Thevenin? Or what's Z Thevenin? We call it Z Thevenin instead of R Thevenin. What is it? It's 3.9K plus what? The parallel combination of 500 in parallel with this 2237.89 at angle 34.01. What is that? And how do you find this? It's the 1 over 1 over 1 over 1 over 500 plus 1 over 2237.89 at angle 34.01. What is Z Thevenin? I'm sorry I had to go out there, but I did. You guys figured it out. I've got the answer. You figured it out. Who did not get a copy of Lab 5? We're going to go through this as well. Okay. Can I get a copy? Lab 5? So what do you get for Z Thevenin? Isn't this fun? Believe me, I want you to get through this and understand this. This is terrible hard, and I don't like it, and I tell you, I didn't like it when I did this course. You'd say, why did you have to do this? Why do we have to do this? After we get through the midterm, there's some other stuff that we're gonna do that's, I hate to use the word fun, but it's not like this, okay? It's not dreary. I promise you, this course will end up with some decent stuff, and you'll end up with some very interesting things to do. It won't all be like this. But we gotta go through this. We gotta understand how to do this kind of stuff. All right? So, what is the answer for this Z-Thevenin? I get 419.5 something at angle 6.02. All right? And then what is VB? It's the voltage then is, you rebuild this, you put this in like this. Yes, sir. Huh? You have to add it because you're starting here and you're walking back to here. You have to add it in. You start R Thevenin by walking from this point and coming back to this point. And you've got to put the 3.9 in, and there it is. There's the 3.9 plus this. Okay? It's 3.9 plus the parallel combination of this and this. And here's the 3.9, and there's the 500 in parallel with the 2 point da 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 da. That little double, the railroad tracks means parallel. If you've not seen that before, that's what that means. All right, so you come up with 419.54. So now you've got this circuit, right? With this is this resistance right here. And now you add back in the capacitor, which is what? What's the capacitor value? You've forgotten because it's so far back in your history that you don't even know what it is, right? Right there it is. So now you say VB is equal to what? Minus J1K over, what rule are we using? Voltage divider. Voltage divider is your best friend. It's 1K minus J1K over minus J1K plus this Z, this whole Z, that whole Z right there, which is that. So it's this, it's this over this plus this times that. And this isn't the 30, this is the V Thevenin. All right, V Thevenin, Z Thevenin, minus J1K. Put it back in. So you clipped it out, took scissors and clipped it out. Now you take Scotch tape and put it back in. I hope it holds. It will, and it works. Any questions, any comments, any concerns? Can you do this? Please work on this one. Yes.
I still have one more question. So it's the same thing that he asked. So we do 49K and why is it 5 years? 3.9. There's the-
Okay, Z Thevenin is, okay, so I'm, okay, so it's, okay, so I'm looking at it from the right. So I'm coming at it. I'm coming at it from up here. So I'm walking in from here. Okay, I walk in the door here. I come through the 3.9K, right? Then I come down to here. Now what is this? This is this. Okay, but it also goes this way. So it's this in parallel with that. So there it is, the 500 in parallel with that. So it's 1 over 500 plus 1 over this. That's the parallel combination. Yes, then it's plus, yes. This here is just this. Then you add the 3.9K to it. And that gets you the 419, yes, yep. Any questions? Any comments? I know, this is not what you paid good money for to come to the University of Toledo to learn. But on the other hand, this gets you a good background in how to do complex number questions, and it also gets you to the point where you kind of understand how phase shifts work and all that kind of stuff. And they do happen in the real world. So you can kind of understand a little bit about what is going on. This is not easy. That's why we're doing it now. Toward the end of the semester, we have some other stuff that is not nearly as hard, more easily grasped, and does make it helps to make this make a little bit more sense, okay? All that being said, I can't say it enough. The calculator is your best friend. This calculator will bust through these questions without you having to break too bad of a sweat. You get a calculator that does not do this kind of stuff, you will have major problems. The calculator gets you through these. If you have a good calculator, it's not hard. It's not as hard as it once was. Okay. I know we can just wave our hands and say, this is nice stuff, and you can understand a little bit of it, but to get down into the nitty gritty and be able to write problems like this and be able to solve them, it gets you an understanding of how phase shifts work, of how things work in the real world, and it gets you to a point where you can take tests for the fundamentals, for the PE test, and get questions and knock the thing out and have PE after your name, because this is the kind of questions they're going to ask. Sorry to say it, this is the level of what they're going to ask, but this is what they ask. Any questions, any comments? We need to get through the lab. Okay, so that's 5.37. Oh, by the way, what is VB? Did I give you the answer? What is VB? My answer is VB is equal to, it's minus 1JK over minus J 1K plus 4317 at angle da 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 da. And its final answer is 5.692 at angle minus 71.492. Or that's what I got. That's the final answer. That's VB. So for problem 37, that's the answer. Yes, sir. This is this my Z Thevenin is my Z Thevenin is not this. My Z Thevenin is 4317 at angle 40 point at angle. Yeah, I wrote the wrong number down. No. My Z Thevenin is not this number. My Z Thevenin is 4317.4 at angle 0.58. That's my Z Thevenin, not this. I'm sorry. that the combination of this is 419.5 at angle 6.02. Just this part. Then you add the 3.9K, and that gives you this whole total number there. And that's this number right here, which then equals 5.692. That's that. I got too many things going on. All right, lab number 5. Let's go through it a little bit. These get hard, and we actually take multiple weeks to do lab number 6. So this is an inductor. This is just like what we did the other day with the capacitor, but it's with an inductor. And with inductance, as the frequency goes up, the resistance goes up. Okay, so, and they use a 10K resistor for R. So this is the same kind of circuit as and there is a R in there is a resistance in the inductor. And you measure the DC coil resistance of the inductor by using an ohm meter. So you use the ohm meter on your meter of your old DMM to measure it in ohms, to measure across it to get your resistance of the coil, which is added to the resistance of the R. But really, you don't worry about it. You just measure it, but you don't do anything more with it. Okay. So here again, you do the same thing you did in number 4. You use the magnitude, because they put such a high resistor there for R, you can ignore the reactance of the inductor, determine the circulating current measured by saying 10 divided by 10K, or what? 1 milliamp. Peak to peak, 1 milliamp peak to peak is I. And then you take that and take your V, you measure your V divided by your I, and that gives you your X. All right? There is no J in that X. You could drop the J. Once you say, well, there's supposed to be a J in there. I know, but you can ignore the J, all right? Sometimes you can, sometimes you can't. Here you can't ignore it. Okay, enough. You know, in a way I feel bad. I'm sorry I had to take a phone call. I did. But this kind of problem is the worst problem you'll have, I promise you, on the test. But you will get one like this. It won't be exactly like this, but it'll be something like this. It might not include 2 components where you have to combine 2 there. It might. I can't promise you one way or the other. But to find a Thevenin circuit like this is not uncommon in a test. All right? Like I said, next week, we'll get through chapter 5 and chapter 6. We'll get through chapter 5. How's that? And probably, I don't know about chapter 6. But next week, probably Tuesday of next week, I'll give you a practice test. We'll talk about more of these problems in chapter 5, the Thevenin and Norton. But we'll get you a practice test probably on Thursday, which you can work over the weekend. And we'll come back the following week 7, and we'll work through it together. Okay? We'll work through it together. And at that point in time, you should be ready. If you practice this stuff, you will get it, and you will get it pretty good. And I promise you, if you do work at it a little bit, it doesn't take long for this stuff to start coming around. But first time through it, it just looks like, well, it doesn't look very promising, does it? But there's some rewards, not a lot, but there's some. The best reward that I can tell you is that this is the kind of stuff that you do get on your PE and your fundamentals test. And it does explain things like when you walk into a factory, how, why they have to put capacitors in to bring down the current in a, and to preserve, to keep the energy in, to minimize the energy usage in your factory. You have to complement a capacitor, or you have to complement the inductors, which are motors, with capacitors. So all the time, you're hanging capacitors on a motor starter circuit. Because why? Because it brings your current down. It balances, it takes that imaginary part of your current and brings it down to zero, because if you can begin to see that the minus J cancels the plus J. And that's what happens. So you bring the current down by putting some capacitance in it, and then all of a sudden you bring it down close to zero. So you're having pure resistance to the best of your ability. And that's how you can maximize the power that is used in your plant. That makes sense? So there is some rewards to this. It's not like there's nothing here. It's not like, will I ever use this? Probably not. You will on the test for me, and you'll use it on the PE test. If you want to take a PE test, it's your choice. You want to be PE? It's your choice. You don't have to. Why? If you're a doctor, you have to pass all kinds of tests. If you're a nurse, you have to pass all kinds of tests. You have to qualify, right? There is the industrial exemption for engineers. Basically says you don't have to have PE behind your name in order to practice an engineer. You don't have to. All right? You don't have to do that. If you want to, you can, but you don't have to. What does PE behind your name mean? Is a PE? Can be sued. More likely to be sued. All right? But on the other hand, if that's something you want to do, here's the path to it. But I can promise you that the practical side of this is it's there. If you work in a factory, if you work in an industry, they will say, design a motor starter center. And you go through and you put all this stuff together. Then they'll say, did you add the capacitors? And if you give them a look like, why do you have to have capacitors? It's like, what does that mean? Oh, you didn't take a course where you had to do this stuff. That makes sense? This explains why you have to add capacitors in order to make your motor currents the less. Bring them down to where they're the minimum, to where you're getting the bang for your buck. How many of you would like to take your billfold out and spend $1.40 for $1 worth of something? Okay? That makes sense? That's why you add capacitors to motor circuits in a factory. It's about the only good explanation I can give to why you study this stuff. And that's not much. I can explain that in about 2 minutes and you got it. But the why and the underneath belly of it is right here. Why this works and why this makes a difference is right here. Because you can see these phase shifts. You can see them, right? You can do this and this and this and this and this, changes things. You add this, it does this, it does this, it does this. Why does it do it? Right here it is. This is the answer. All that, quarter sometimes gets you a cup of coffee. I apologize to a certain extent for doing this to you, but on the other hand, there's some good stuff coming at the end of this course. I promise you that we'll liven the course up. And you learn this stuff, and it does help you understand things that, and I'm begging you to learn this stuff. I'm begging you to spend the time to learn it, because it will help you. But I'll see you downstairs, or I'll see you up in lab in about 5 minutes, because I got to pack up. But on the other hand, here's the stuff that went around if you missed it. I'll be in lab, okay? I'll report, there's, 4 I did not grade yet. I did not grade 4 yet. Thank you, thank you.
Sharing notification, putting my